me get this
All
back.
right.
Oh my goodness, this is just a rock and roll city here. This is let's see, virtual Dan Eric. There we go. Quick play. There we go. Beautiful. Awesome. Wow.
Now we've got Adam.
So we are in our we're at 5.5 hours or so right now. We're going for. I want a Guinness Book of World Record thing here. That's what I want to do. But we should have done that. The longest virtual astrophotography session thing on YouTube.
You know what? Maybe we could make this a thing. You never know. And start attracting more and more people. Maybe this can almost be like the virtual NEAF.
Yeah,
or
absolutely. And you know what I'm going to do? I'm going to put a poll because I haven't done a poll too much today. Do you want to see AstroPalooza 2 in 2023?
Are you not entertained?
Are you not entertained? When you wake up and you see fields and the sun shining in your face, it's all right because you're in Elysium and you're already dead. But anyway, that's you know what. And that being said, and right before the atom block, we just gotta there you go, be off the rails. There you go. But for those of you that have been waiting for that, there you go. But let me see, quick play. There we go. The rail. Yes, no shots yet. It's still too early. I'm staying sober. Come on. Water is all this is. It's way too much work. This is awesome. It's a lot of fun. It's great people that we're talking to, and all the guests have been awesome. Our next guest, unfortunately, is not able to come to us live due to prior commitments, but he wanted to be a part of AstroPalooza, and he did send us a video. Now, the video is a little long. It's about an hour, but it's Adam Block, and he's talking a lot about Pixinsight and some tips and tricks. If you're interested about that, stick around because we're going to do 2 more giveaways first, and then we're going to hit up the Adam Block video, and that'll run to about 8:45. So I just want to put that out there for
9 Eastern.
8:45 Eastern. Yes, please. Thank you, Eric. Eastern, 8:45 Eastern. And Tom, if you're watching, that's when you'll come on at 8:45. So at that point, that would put us about. Oh wow, we got 2 more guests after that. So we got Tom and Charles. So
I mean,
awesome.
We're getting towards the home stretch here, but it's all good. And you know what, Adam is a wizard when it comes to Pixinsight. So
he really is. He is awesome. It's
going to be working.
You know what we're gonna do? We're gonna do the giveaway for the AstroWorld gym bag. How about that?
Nice.
Let's do the giveaway for the AstroWorld gym bag. Here we go.
Let's do it.
AstroWorld gym bag. Here we go. The gym bag goes to Dominic McKellar. Dominic.
You forgot to bring it up on the screen again, but that's okay.
Oh, I'm sorry. Come on, man. You're supposed to get me on that. There you go.
That's true.
Dominic McKellar. There you go. So I could show it so I wasn't cheating. So Dominic McKellar, you will be getting an email from me, and we'll get you that gym bag. It's pretty cool. It's nice and big. Pretty cool.
Someone was asking, will a tripod fit in it?
No, it's not that big. It's not a duffel. It's a gym bag, so it's not that big.
So hey, you can look stylish when you're heading out to the gym there, though.
You can. It says a nice AstroWorld kind of logo on the side. It's pretty cool. So awesome. So we got that done, and then what we're going to do now is we are going to start up the Adam Block.
Wow.
Wow. I'm skipping two guests here. Adam Block's video on Pixinsight. So let's get that. What do you say, Eric? Let's roll that what?
Let's roll that beautiful bean footage.
There we go. Awesome. Here we go. Rock and roll.
Hi, this is Adam Block. Thank you for giving me this opportunity to speak at AstroPalooza. This presentation is about Pixinsight, specifically about the usefulness of pixel math. It's just a quick introduction to pixel math and how you can take advantage of it, and show a quick couple of demonstrations that are unique. So I hope you enjoy the presentation and have a great time. So let's begin right away by looking at pixel math. Now, I'm not going to be able to show exactly how pixel math works in its entirety in this video. I'm just going to highlight some aspects of it that will be useful to demonstrate some of the great power in terms of diagnosing a problem or addressing some kinds of misconceptions, other things. I've got some really good examples, and I'm going to be using pixel math to help illustrate how powerful Pixinsight is and how you can figure things out. In order to do that, though, I'm going to give this introduction to pixel math very, very basic. It won't be full, but it'll be just enough to get me to be able to illustrate some of the examples that I would like to. If you haven't had an introduction to pixel math before, it is my hope that this really gets you thinking on the right path. So let me begin with the name. Notice that the name says pixel math, not pixels math, because it does indicate exactly how it works. Pixel math visits one pixel at a time in your image, and then it loops over all pixels. It visits all the other pixels. Now, when I first learned about pixel math, I somehow correlated the number of pixels that are in my image with the complexity of the tool. In my mind, I just thought, oh, I have millions of pixels in my image. The tool must be doing something very complex. And the true answer is it is the exact opposite. You do whatever it is you ask it to do, one pixel at a time. So you can simplify all of the thinking, all of these fancy expressions that you ever see people use. You may have copied these pixel math expressions. You're just evaluating that expression and doing one thing at a time, one pixel in an image, and that's it. So let me begin actually in that vein by making an image that has just one single pixel. So I'm in the destination area here. I can create a new image with a width of 1, a height of 1, color space, we can make it grayscale, and we'll just make it a 16-bit image. Nothing special. There is something you should know, though, about Pixinsight, if you don't already know, which is that the values that we work with in the program, they go between 0 and 1. So 0 would be a black value. White would be a value of 1. And then you have all the grayscales in between. Halfway is 0.5. So I need to say, if I'm going to make a pixel, an image that has one pixel, what value do I want to give it? So pixels have two basic characteristics. They have a value, and they also have a position in the array. Now this array will only have one, so there's really no position to worry about. But I'm going to say 0.5. This will make it a gray pixel. Now I'm not going to be using the triangle. This means to drag onto another image. We don't have another image. The square means apply to an image on the desktop. We don't have an active image to apply to. So the global apply here, this is the one that says, please execute everything that we've set up here without interacting with any other image. We can do that. So I press the button, and we get a single pixel. Now this looks like, it looks like an image, right? It's not. Look at the zoom factor here. We're zoomed in 100 to 1, right? This is literally a single pixel. If you look down at the very bottom, you can see the value here is 0.5, and the position is a value that is less than 1. And I'll explain why that is in just a moment. But what we did is we put 0.5, and then we generated this image here. If I want to change the value and make this a white thing, I need to replace my target image. Now I can drag this triangle to a target, and it'll put this, this number 1, the value, into the pixel, makes it white, or makes it black. Now this is not terribly exciting, I understand that. Let's make it a little more exciting here by creating an image with 2 pixels. Oh my goodness. Now we're going to have 2. We'll have them initially both be black. If I do this, now we'll get a rectangle. Now this again, you got to keep in mind, I'll stretch it, but look down at the bottom of the position. This position here has a value less than 1. Just look at the X. The Y isn't going to change because there is no Y. There's only a horizontal row here. So we have a value here of less than 1, and then we have a value here greater than 1. This is the position value here. Whenever you have an array of images, this is like a computer science thing. It's an indexing thing. Positions, an index of an array begins at 0. This is the position 0. This is the position 1. Notice we have 2 elements, but the actual index goes 0 and then 1 for the position of these pixels. If I wanted to show you that we are actually looping through, when I put this, 0.6, whatever it is I put here, and then I say, please apply that to this image, we are literally doing the following thing. We're saying, please put 0.6 at the first pixel, then go to the next pixel, please put 0.6 to the next pixel, then go to the next pixel, please put 0.6 to the next. It's really boring, right? But let's do something a little different now. Now let's visit every pixel and use the fact that they're at a different position to do something differently. We can use the looping capability to do something based on position. It's not the most common thing to do. Generally, you're acting on all the pixels based on maybe some other image, right? But in this case, I'd like to correlate the value of a pixel with its position in the array. There are reasons, and we're going to be using one, to do this sometimes. So I need to now show you that there exists functions. It's under the expression editor. You can click and see that there are functions and operators and all kinds of stuff. This is a reference that you can use. You can pick and choose from any of these things here. It tells you basically what it does and how to utilize it. Most of these functions will have the name, and then you put whatever it needs to do its job in the parentheses. Some functions don't have anything that you need to put in there. They just do the thing that you ask them to do, and the one that I want to use is of that type. Down here, there's a small x, and it has a synonymous name of x position. That's what I want. I want to know what position we're at in the array, and then we can do something at those positions. So the function I need, I can just say x and then put these 2 parentheses, and I can use that function to get the answer that I want. Now I'm going to put more than 2 pixels. I'm going to try to create an image now that has 4 pixels. In fact, I'm going to think ahead. I'm going to just solve this right now. I'm going to put 5 pixels. You'll see why I do this. I'm being a little sneaky here. And we're going to first make them all be black. So we're going to get this wonderful rectangle. We have 5 pixels here. I promise there are actually 5 of them right here. But in this time, we're going to visit each one, and we're going to put its value of its position as the value, the brightness of the pixel itself. Let's just see how that works, right? We'll do this one first. The first position is what? It's 0. So when I ask it, please give me the answer to this thing reports the answer to the position. So for the first pixel, the position is 0. That means that this value is 0. That's what it's going to put here, is 0. The second position has a value of 1. So this will evaluate to the number 1. So it'll put 1 here. That means now I have a black pixel and next to it a white pixel. The next pixel over has a value of 2. So 2 is bigger than 1. That's actually an issue. Remember, values in Pixinsight can only go between 0 and 1. So if this thing evaluates to 2, what's going to happen? Well, it's not going to put 2 here. It'll just say anything's bigger than 1. It'll just become 1. It clips it to 1. So now I have a second white pixel. We have black, white, white. And that'll continue to happen if we have a number 3 here, a number 4 here. Every time it'll just be white because all the other x positions are greater than the number 1. If I actually apply this now by replacing the target image, I expect to have 1 black pixel and the rest should be white. Let's see if that's true. It is. Look at that. 1 black, 4 white. But let's see if we can be a little more clever about this. Let's relate the fraction of the position that we are at to the color that we apply to that pixel. In other words, if I divide by 4 here, watch what happens. And you might want to pause the video and just do the little math in your head, and you can see what is about to happen before I do it. But here's the way to evaluate the image. The first position has 0. 0 divided by 4 is what? 0. The second position has a value of 1. 1 divided by 4 is 0.25. Now we're going to have a gray image, a gray value in the second pixel. Then we'll have 2 divided by 4, which is 0.5, a little bit brighter, half. 3 divided by 4 is 0.75. 4 divided by 4 is 1. So we should have this little mini gradient, actually, of pixels when we apply this expression. Let's see if that's true. And that's exactly what we get. What I've just demonstrated is how to create a gradient in an image. Now, this idea of dividing by 4 by scaling by the fractional position in the image is actually a function in and of itself. I'll show it to you. It was right next to where we were. It's a capital X. The capital X says return the normalized horizontal position in a range between 0 and 1. That corresponds, of course, to the fractional position that I just specified by dividing by 4. So if I instead put a capital X here and then ask for the result, we get the same thing. It's the same answer. Just to prove to you that it is really the same answer, because it didn't change. First, let me make them all back 0 again. Then I'll put in this capital X, like that. And there we go, a gradient. So I hope that you've learned an awful lot of things here. But the most important thing I'm trying to express is the idea that whatever it is we put in here, we visit each pixel and do something based on whatever the expression is here. We're just visiting one pixel at a time. You evaluate things one pixel at a time. With this very basic introduction, I can now begin to show you how to think about solving some very powerful, easy things in Pixinsight that are the kinds of questions that I often get, actually. I'll show you some examples. So now I'm going to completely switch gears, but I promise you we're going to get back to pixel math in just a moment. This is a very common question. Many people have this question in some form, one form or another, but this is a pretty dramatic example. So an individual sent me an email and says, Adam, look, I have this image that looks pretty good before I apply DBE. DBE is dynamic background extraction. It's supposed to help remove gradients, right? So this is the before DBE. And then he has an after DBE that if I click on the image here and we do page down, you get an answer that looks like this. And he's like, Adam, look, DBE is messing up my image. What can I do? What parameters can I do with DBE that will not give me this result? Because if you look at the original result, it doesn't look anything as bad as this. Help me, Adam. Help me, Obi-Wan. What can I do here? Well, one of the things that I would say is that this is not a DBE problem. This has nothing to do with DBE. The point is that when you look at an image that looks like this, that information, that noise, those vertical crazy things, whatever those things are in the image, they were always there. And when we're looking at the image in its uncorrected or less corrected form as far as DBE is concerned, it's just that the brightness of the sky itself is overwhelming the information that we're seeing here. When we remove the gradient and we redisplay the image in some particular way, we're going to see these lower level effects that were just not obvious before we had removed the brightness of the gradients and so on. So there's two different things. One thing is that the information is harder to see when we have this brighter values associated with the sky brightness or the gradient, whatever the case might be. And then we have this other issue of the fact that once we have adjusted the image with DBE, we have a completely new set of pixel values. And those pixel values are going to be displayed in a different way using the tool that is the screen transfer function. This is what's used to display this image. Now, the images that I'm showing you here are actually screenshots that were given to me by the person, so I can't show you the transfer function on the screenshots here. But I'll show you basically the same idea in an image that I'm going to recreate for you. I'm going to recreate the problem so that you can see it's not a DBE problem, it is a data problem. And by the way, the data problem that is here, I mean, this could have a number of different things going on. It could be everything from an electrical problem to a certain kind of fixed noise pattern problem. All kinds of particular problems can cause this, but it is not a processing problem. It is truly in the data, and that needs to, of course, be solved. So I've tried to manufacture what is a typical astronomical image, all right? So pretend with me that this is a picture. This is a picture of a nebula. It really is, right now. You can't see it. You can't see it because let's say you took this under Bortle 8 skies, right? And so when you initially take your picture, the sky brightness is just so bright that all you see is basically a gradient. And then we need to remove this excess light, remove the gradient so that we can see the nebula, right? So the way that people remove gradients is, of course, they are going to use a dynamic background extraction. So that's what I'm going to use here. I'm going to get out dynamic background extraction. And I'm not going to worry about stars because there are no stars here, right? So we click on the image. I can make the tolerance very high. I can set my sample radius as 5 is fine. I'm just going to generate a whole bunch of little, samples across the image. And that should be able to remove the gradient, right? So we're going to do subtraction here. And then I'm going to go ahead and just say, replace target image. And then we can see, hopefully, the adjustment that occurs here. Ready? Aha. So once we have applied DBE, you can see the nebula now that we couldn't see it before. Now, why couldn't we see it before? Remember, let's just go undo here. If I go well, let me do this. Sorry. Here, if I go back a step, this is the auto contrast version of the image. I did the auto STF because the gradient is so bright, so much brighter than the nebula, my little smiley face nebula. You can't see it in here. The values of the nebula are just, 0.001, whatever they are. But the nebula values here, or not the nebula, sorry, the gradient values here are 0.2, 0.3, whatever these values are. They're very, very big compared to the nebula. So only when we remove the gradient can we see the nebula at all. Here's my little smiley face nebula. But notice that there's also the noise that you can see there as well. The noise, the vertical columns that you see in the image, they were there all along. DBE did not cause that effect. They were already in the data. This is exactly the same thing that we're looking at when we look here. It is precisely the same. It's not a DBE problem. It's not a processing problem. This is in the data. But people oftentimes will associate the result with a processing problem. And I'm trying to say it isn't a processing problem. So what I'd like to do is just reconstruct. How did I do this? How did I get that result? Well, I can show you precisely how I did it. It's not hard to do at all. The first thing we want to do is we want to create the problem. Those vertical lines, we can actually create vertical lines in an image. It's easy enough to do. Let's just make a new image here. We're going to make it 1,000 pixels by 1,000 pixels. And let's make it, grayscale image. And again, 16-bit. Well, you can even make it 32. Doesn't matter, really. Make it 32-bit. Floating point. There we go. Because that's typically what the kind of images that we work with for astronomical images. And then what we're going to do is say, we'll use a function. So what I want to have happen is if you looked we had all those vertical lines, right? So that means that whatever that effect is that we're seeing vary, and it's varying periodically, it's doing so in the horizontal direction. There's no variation in the vertical direction. It's all horizontally varying. So what periodically varies, what function periodically varies at all? Sine and cosine, right? I'm going to use cosine because I just like it. So the cosine function varies. And so what do I want to take the cosine of? Well, I want to take the cosine of the position that we're at. For every pixel that we are visiting, we can say, report to me the cosine value. If I actually do that, we're going to get some kind of variation going across the image. So let's just say, for example, I said, give me the cosine of the x position, right? And let's just say that's all I ask it to do. Just give me the cosine of the x position and give me that image. What do we get? We get a crazy thing which looks like this. You can see that we are getting this, function variance going across the image. But if we want this to be like what we saw in the, with respect to the nebula, it shouldn't be very bright. I mean, these values here go all the way to a value of, like nearly 1 and so on. So we need these values to be very, very small values. Let's go ahead and replace this, and I'm going to basically just multiply this number by a much, much smaller number, 0.001 or something like that. Then this will have very, very small values. In fact, if you just display the image in this form, you can't see anything. You actually need to do the auto stretch in order to be able to see the problem. And there they are. The next thing I want to do, and again, I just want to make this kind of like some kind of noise-like thing, right? I'm going to go ahead and blur this a little bit with convolution. So we get the convolution function. I blur this. Maybe we blur it again or something like that. So now it's a bit blurry. And then we can add a little bit of that noise to this image as well, right? So I can again do the auto stretch, and you can see the result here. Every time we do an auto stretch, the darker I make the image, the more contrast the auto stretch will become, because that difference between bright and dark things becomes more important for the very, very faintest pixel values here. That's something to keep in mind when we look at, when we compare these two images. That's part of what's going on. Let's go ahead then and add a little bit of noise. So I'm going to go to Noise Generator, and we'll add here I already have it set to some small amount of noise to the image. So there we go. This looks kind of like, you can see the vertical pattern in there, barely, but that looks like the kind of noisy result that we might get from a CCD camera, right? So we can call this our noise image. So there's our noise. I didn't spell that right. Now to make the nebula, what did I do to make the nebula? I did the following. I used the game script, and I basically added, a circle in here like this, so I could get like a white circle, and I just made it a binary mask, and I said, yes, please do it. There's part of the answer, but then I needed to put little black things in there. So if I wanted to put my little black things, I just use the clone stamp tool really quickly. So I go to clone stamp. So we click, I want the radius 25, sounds good. Opacity 1 sounds good. So I do an alt click here. Oop, control click, sorry. I put my thing there, and I put my thing there, and then we try to make a thing here and a thing there. So there, oh, that is ugly. I don't even like that last one, but whatever, there. So we go okay. But of course, again, this image is going to be too bright because we have values between, they're either 0 or absolutely 1, but we want them to be nebula-like, right? So if I just multiply this, every pixel here, by a value of 0.001, 0.001, something like that, again, we're going to get values that are very near to the values of the noise, which is what we want. So I'm going to do the auto stretch. I did that wrong. I'm supposed to multiply. So let me show you a new thing that you need to know, which is target T. Target T means whatever image that I point at with this rectangle is the one that I mean here. So I want to multiply the pixel that I point at, whichever image I point at. I could spell out the name of this image here, but I'm just going to say target T means wherever it is I'm pointing times 0.001. That will do what I wanted. There is my little nebulosity. So I have my nebula, I have my noise. I'm going to go ahead and we can add these together if we want and create a new image. So we just say noise plus our nebula. So the name of our nebula here, I'm going to give it a name of neb, N-E-B. So I can do noise plus neb. And this time I'll create a new image. We should be able to do that. There it is. We don't see anything because, again, the values are so small. If I do my auto stretch, you can see the noise and the nebula here, right? But that's not enough. Then we need the sky. We need our gradient. So we can create a gradient out of this image as well. So how do we create a gradient? Well, I already demonstrated that a moment ago. I just made a copy of this image. And if you recall, I can just use that capital X with the parentheses. That's going to make a gradient here. Now this is being displayed as it is because notice there's a green line. We are applying the auto STF to this image, which is not what we want to do. I'm going to reset it, and then we're going to see our nice gradient going across the image. So here's the gradient image, but of course this gradient is way too bright. I don't want the values to go all the way from this to there. I'm going to make it a smaller number. Let's make, all we do is we do target T times maybe 0.3 or something like that. Let's see, replace target image. That should do the job. There we go. So this is our gradient image. Gradient. So now we can add our gradient. Let's call this, I don't know what I want to call this thing. So this is our actual image, right? Now, I'll call this our neb. I already have that one, right? Yeah, neb plus noise. Neb noise. This is our neb noise image. So we're going to say neb noise plus grad, because this one is called the grad. We just add these two things together, create a new image, and there it is. That's what I did. This now has the sky gradient plus the nebula and the noise all together. And then if I did the trick that I did a moment ago with DBE, where we click on the image here, we can generate our point. Let's not generate the points like that. Sorry, let me reset that. We need to have this a tolerance of 10. Then we can generate all of our points. We say subtraction, replace target image, do it. And once again, I chose different values this time, but you can see that we can see our nebula plus that crazy noise that's in there. Close this. Yes. There's our nebula plus our linear kind of noisy stuff. The point is that that noise was always in the image to begin with, and only after we removed the gradient were we able to see the noise. That is exactly the same as the demonstration shown right here. Where if we blink back and forth, we have an image that seems to be worse, but it isn't worse. That information was always contained within the image, and that's what needs to be addressed. So in this next section, I'd like to talk about another problem that came my way that can be solved with pixel math. I had a friend who sent me some data that he wanted me to work on, and I actually made this a tutorial on my website. So there is a complete processing section that from beginning to end shows how I process this image. This is the Whirlpool Galaxy. It's wonderful data from Keith Allred. That's my friend's name. And the reason that he sent me the data in the first place is that he had a problem. So this image would not have worked out nearly this well had this problem not been, diagnosed and figured out. I'm going to show you what the problem is. I'm going to show you how pixel math can help figure things out, diagnose things. This image is enhanced in some sense with some hydrogen alpha information data. So these H2 regions that stand out nicely with the blue, with the pinks and the reds, they are somewhat boosted by that hydrogen alpha signal. So this does concern the HA data, actually. So he has wonderful red, green, blue luminance data, but then there's also this additional hydrogen alpha data that I needed to blend in. And it's the hydrogen alpha data that I want to show you. So let me show you a directory here. And this directory also highlights something else that's kind of interesting. You'll see that I have HA data here, and you see how this has an _1 in these file names, and then I have another set down here where it's just HA, and then you can see it's calibrated, cosmetically corrected, and then registered. So there's two different versions of this data. The first version is, of course, I was able to reproduce the problem that Keith had, and I needed to figure out why it was an issue. I'm going to show you the initial calibrated images. We're just going to blink through them, and you'll very easily see what the problem is. So these are calibrated and registered. That is actually key, that these are registered images. I'm going to press the little automatic display, and can you see this pattern? This is something that a lot of people, many people encounter. And you might think, what in the world is this thing? Is this something wrong with my camera? Is this something going on with the micro lensing? I mean, what is the pattern? Here's the interesting thing. If I blink through the images, you'll see it change from image to image. And then sometimes it won't be there or seemingly not there. But if you notice, it's actually there, it's just really big. And now it's getting a little smaller and smaller until we get back a little bit more of the pattern. So it's almost as if there was like a zoom factor. If you are familiar with moire patterns, that's exactly what this looks like, a moire pattern. I have to pause the video here because I'm not pronouncing that word correctly. I've never really said it out loud that much. So the word is pronounced moire, not moire. It's my ignorance showing here, and I'm a little embarrassed. But every time you hear me say moire, please, in your head, think moire. Thank you. So a moire pattern is one where you have some fixed, usually grid-like pattern, and then you shift the two grids. You might have two different grid patterns, and you shift them. And see, this is already starting to speak the language of what we're looking at. We're looking at registered images. If we look instead at a registered image like one of these, but if we actually looked at just the straight up calibrated version of that data, so once again, I'm going back in time here. I'm grabbing one of the calibrated images like this one. This should be one that's the original calibrated image. You won't see the pattern at all. There's no grid pattern. And yet the same image, I actually opened up this one, the 505 image. This 505 image in the calibrated form has no weird pattern, but when, it's just displayed differently here, but when displayed in the blink tool has the pattern. And of course, if I actually just open up straight up this image, it'll have the pattern. So the first instinct that I had is that there must be something about the registration routine that is causing this problem. And in a sense, that is true. But I want to just stay with this image for a moment. When people get results that look like this, the first reaction is, oh my goodness, WBPP is doing something to the data. And I just have to say, halt, stop. No, that's not the way to think about it. Not really. What we need to do is say WBPP has this pipeline of tasks. Which task, which process could possibly be causing this issue? So it's clear to me that if we have just the straight up calibrated data, no grid, and then we have grid in the registered data, something about the registration process causes this to be a thing. But it's not somehow the registration process itself. It's a consequence of something in the data. All right, so I'm dancing around what's going on here. And now what I want to do is actually show you something about this calibrated data that we're looking at. This image is bad. That's a key insight. This calibrated image that we're looking at, there is something terribly, terribly wrong with it. You may even be able to see some hints of some kind of small scale patterns, not like this, big grid thing, but small scale patterning of some sort. But just by looking at the image, it would be really, really hard to tell that there was something wrong, not without doing some other kind of analysis. So I'm going to go ahead and close my blink thing so I can just take that out of memory. And we're just concentrating on one of the straight up, before you even do registration, one of these straight up images. The key insight here is that this is a narrowband image. And anytime you have a narrowband image, you need to do a check. I have a video about this, but I'm going to again illustrate it right here. One of the checks you need to do is, in the course of calibrating images, it is possible that the sky is so dark, basically, that when you subtract your dark frame from the image, it's possible to get negative values. And to offset that, you want to add a pedestal so that you don't lose data in the process of just calibrating the image. Now, how do you know? You can't know by visually looking at it, not easily. This image looks fine. This looks like a wonderful HA result for M51. It looks fine, really. But let's zoom in and let's roll the cursor around here. And as I do, guess what I find? Do you see how I've got the cursor on a pixel here and it says 0? Let's zoom in some more. There's another 0. Oh, there's another 0. Look at that, another 0. In fact, we should really figure out how many 0 values are there here. Now, when I say 0, what is happening, as I demonstrated in the earlier thing, is anytime you get outside of the range of values between 0 and 1, it just gets clipped at the extreme, either 0 or 1. So any negative values in the course of doing calibration are going to become zeros in the calibrated result. So how many zeros are in this image? If there are a lot, that indicates to us that we need to have a pedestal in order to calibrate this data properly. It is common to require a pedestal when working with narrowband imagery. Let's get out pixel math and demonstrate the whole thing. So pixel math, I don't even know, here it is. I'm going to clear what I have here. And what we're going to do is search for zeros in this image. So you know that whatever expression I'm going to make, it's going to be look at one pixel and evaluate the expression to see if it is true or false, and then do something. Because we want to know, is it a 0, this pixel, and then go to the next pixel? Is it a 0, and go to the next pixel? Is it a 0? We need to ask that question at every pixel in here and then do something to indicate visually that it is marked as a 0 value. So the first thing I'm going to do is I am not going to use a single expression. My intent here is that I'm going to light up each pixel that is a 0 in this image as being colored red. That's what I'd like to do. So this is the red channel. The tab now that was our original first tab is now one of 3 tabs. We have red, green, and blue. So now we're using this as 3 different tabs. And I'm going to go ahead and change the green and the blue tabs. We're not going to change this image. We're going to make this an RGB image. Let me go ahead and do that. I haven't done it. We need, right now, this is still a grayscale image, but we can change the image and convert it to an RGB image if we want to. See, we can convert RGB color. And all that does is it means that this image is now comprised of 3 values instead of 1. They're identical. Can you see it says RGB there? So now I can do my cool trick. All I'm going to do is just say, when I drag this over, it means this image right here. I don't want to touch the green channel. I'm not going to touch that value. I'm not going to touch the blue value in this image at all. Oh, I'm not trying to drag it over. I'm trying to say target T. I'm not going to touch that value either. The only thing we're going to say is that if it's a 0, then we want to light up that pixel as being 1, the brightest possible value, but it will only be brightest possible in the red channel, which means it'll be a red pixel. There is actually a function called if. It is IIF. That is the function. and then there are three components to the statement. You need to say the thing that you're evaluating, that's going to be if it's 0. Then you say, then do something or do something else. So those are the three things we need to put in there. So we're going to say if the value at the pixel, so if it equals 0, that would be target T. If the value of the image, that is that pixel that we point this at, if it equals 0, now equals in this case is an evaluation. It is a Boolean. If it's true or false, you need that little double equal sign there. We're not saying if it equals, like we're not assigning it a number. We're saying this is a conditional statement. So if that pixel equals 0, then we're going to make the value for it be 1. Otherwise, we don't touch it. And don't touch it means we just keep whatever value it is. That's just target T. That's whatever value that pixel was in the image, it'll stay as that. So that is the whole expression. That's all I need to do. If it finds a 0, it'll make it red. Otherwise, it won't do anything at all. And it's not going to do anything at all in any of the other channels. So we should be able to replace the target image, and I hope you're impressed with the result. That, my friends, is not a good sign. Every single one of these red pixels is a 0 value in this image. There is very little data here. The process of calibrating this image caused the problem. So why did we get that weird moire pattern? It's because the only things that survive are the things that are brighter than, that average low level of whatever the dark frame was, which are kind of like warm or hot pixels. In the course of registering the images, all of those little warm and hot pixels are in the same place, and they get shifted a little bit just by the process of interpolation and translation and everything that's necessary to align the images. That's what caused the moire pattern. But the ultimate cause is that we are subtracting most of the image away, and we're only leaving, some of the brighter pixels of this image. So now let me demonstrate that once I added a pedestal, I'm going to open up here. Let me just open up WBPP so you can see where the pedestal gets added. Now I probably have some other project loaded in here. Here, I just opened a few files just so I could light up this section. This is where you can add a pedestal value. You can either put a literal value, which would be something like 200, I believe that's what I used in this case, or you can have Pixinsight calculate a value based on a limit and all of that. So it can try to find the value that does not result in very many negative numbers. Both of those will work. I actually like the literal one, just as long as it's big enough, you won't be doing any harm. And that's where you input that. Please watch my video on this whole subject concerning the pedestal and how to use it in Pixinsight. But what I want to prove to you is that if I open up one of the calibrated images that I did with the pedestal, in fact, I'll open the same image, let's be sure. So this one was 505. So if I open up 505, that was calibrated the second iteration. Let's look at this result. And now I'm going to apply the same tool here. Same function, everything. You're going to, I'm going to do a step back here. I need to make this again my view, edit, image. Color spaces, yes, convert. I want to make them red, right? Make them red. There we go. So I applied here. If we scroll around, we can probably find 1 or 2 zeros, which is not uncommon. There's 1, right? There's 1. That's fine. And this might not have anything to do with the dark subtraction as much as it is just hot pixels that are in the dark, that might be an older dark, being subtracted from the data. That can also cause negative values. But it is not because the pedestal is not good. This pedestal is fine. We have all of our data, unlike this image where we're not using all of the data at all. So this one expression, pixel math again, comes to the rescue, and I can easily diagnose an image. It's a quick test to be sure that my narrowband data is giving me good results. I just need to test at least once to be sure that I'm not getting these kinds of negative values in my calibrated images That would be an important test to do. Otherwise, you're losing information and you didn't know it. And I don't mean like a little information. I mean a lot. Let me very quickly show you one last example of how powerful pixel math can be. Sometimes there is a necessity. There's something you'd like to be able to do, and pixel math can basically come to the rescue. And here's a good example of that. I think that this is something that demonstrates this introductory way of thinking about using pixel math. So sometimes you have an image like this. These are some bright galaxies, and perhaps you want to employ something like, as an example, HDRMT. There are certain processes that you could potentially make an adjustment, say selectively, locally on the image, not have to apply it globally, because it just doesn't do anything for a global application. And in some particular instances, like HDRMT, it actually matters that you select an area to work on, because it depends on how large the area is as to what you get back. So to make that very clear, I'm going to make a preview here. That's the area that we'll examine in this image, right? So here's the preview. And the idea is that if I have an image that is like this, now this is already, just so you know, this image is already nonlinear. It's already stretched. And I'm going to apply HDRMT to the image, right? And so I can see, hey, neat. Maybe that's what I like. Now, this is not optimized, okay? But just say, I like that effect. I can see the cool stuff going on in the galaxies. What I'd like to be able to do now is just say, hey, just put it right here. I'm done. I want this effect, my preview, to somehow just get instantly in situ, put right into that location. That's not something that's easy to do, actually. You need to figure out a way to do it. Pixel math can actually do that trick, and I'd like to show you how. So let me go ahead and just demonstrate that. But I just wanted to demonstrate there's a real world reason why you might want that to be true. So let me just demonstrate how you can go about doing that. I'm going to make a destination image here. I'll create a new image. You've already seen me do this before. 1000, 1000. We'll make it a grayscale image. We'll keep it a 16-bit, whatever. And let's make it a white image to begin with. There we go. So you've seen that trick before, right? Now, what I'm going to do is I'm just going to draw randomly here a preview. In the preview, I'm going to change it in some way. How about I do a Control-I? That'll make it black instead of white. Now, what I want to have happen is now that I've made my funny change, I want to get this information into here. Well, now this is not, believe me, this is only for instruction, okay? I'm going to make this much easier in a moment. But for instructional purposes, I need to know the information about this preview. I need to know how big it is, the true dimensions and position in the picture itself. So if I go to modify preview, I get the 4 numbers that I need. The first 2 numbers are 464 and 480, and those correspond to the position in the big picture. And then we need the width and the height. So we have the width is 230 and the height is 306. So I now basically have what I need to know in order to do this trick. So at the moment, we don't have a means to do this, so I'm actually going to drag the preview out here. This is actually a second image now, all right? And this second image we're going to call, I don't know what I'm going to call it. I'm going to call it tiny. It's our tiny image. There, tiny image. Small image, something. So here's the idea. One of the things that you can do in pixel math is you can set up little variables. They just hold information. They can hold numbers, or they can hold an entire expression that can be calculated. In this case, I'm just going to make things look pretty, and so the variable is going to hold the position. So there's an x position, but I need another x position, you'll see in a moment, that refers to the positions of the top left corner of this box. That's what the first 2 numbers were that I just mentioned. So I need a y position as well. Y equals this y position thing. This is just the xy position that when we raster through an image we're currently looking at, right? Now I need an expression. What is the expression that I'm going to make here? Well, what I need to do is when we go through this image, I want to write this image the moment that we're inside of this rectangle. So basically I want to put pixel number 1 right there. pixel number 2 of this image will go right there, pixel number 3. So the moment that we're inside the rectangle, it starts writing these pixels. So there is a way to determine if we're inside a rectangle. There is a function that is called inrect. You can look this function up. It's in the list in that library of functions. And inrect has the following parameters. It's the same parameters that we just wrote down that are for the preview. It's going to be that initial top left corner X and Y position. So I'm going to give those a special name now. That's going to be X0, comma, Y0. And then we need a width and a height. And I forget which is, hang on, which is what here? I always forget. Let's be sure. Modify preview. It is width and height, yes. So we put width here, comma, height. Now these are going to be variables too. I will initialize them or name them here in a moment. But I'm just writing the general form. Then we're going to do this following thing, where if we're inside that rectangle, right? And I didn't actually put the if, did we? If, there it is. If we're inside this rectangle, then we're going to do something. What we're going to do is we are going to write this picture. There's another function. It's called pixel. You can actually write the pixels in of a particular image. So we have to give this a name, and we already have a name here. It's tiny image. Tiny image. And then we need to specify an X and Y position. So I'm going to just put XX and YY here because I don't know what that is. I'll explain why in a moment. And then we need a final condition, which is that if we're not in the rectangle, if we're not in here, then what do we want to do? Well, we don't want to change anything. So remember, this is going to go through the image, and it's going to go and only write these pixels when it's inside of this particular area, right? So we want target T, which means whatever image I point at, those values are going to be put here. So it won't change anything at all. So here's the problem with this X and Y thing here. If I put X and Y, like this X and this Y, it doesn't work. Just look for a moment at what happens. When we get to here, so right now we're not inside the rectangle, right? The moment we get inside the rectangle, that's what this statement does right here. The moment we're in there, what is our actual X position? What does the variable say right here? Well, it's going to be 464, right? So this is saying put 464, put the tiny image at pixel number 464 at this position. But tiny image doesn't have a 464. That's already starting to get outside the image itself. When we write tiny image here, this image here starts at 0. It doesn't start at 464. So what we actually need to do, because it's like an offset, is we need to take whatever our starting position here is and subtract it from this value. Because we are physically at this place on the big chip, even though in pixel here, this function is referring to the other image. So what we need to do is subtract minus our x0 thing and say minus our y0 thing. And that is the whole expression. That's it. That's everything. But I need to define these things. So we come over here to symbols, and I will say x, comma, y, comma. We do x0, and we can actually give it the number that we know it to be here. We can just say 464, and then we say y0 equals, I wrote this down, that's how I know these numbers, 480. And then we say width, and again, I wrote down the number, it's 230. And then we do height, and then equals 306. So I will come back to here and make sure, yes, I wrote height, I wrote width. If I actually go to the expression editor to be sure that I've written everything correctly, I can just go to symbols here and I can say parse. If there were a problem, it would show an error there. And this also, I can parse these statements here and make sure that they are correct. And it says that they are correct. So the whole tricky part of what I just did was this little part here. You just got to understand, and this is actually key to understanding how pixel math works. That's why I wanted to show this example. When you go through the image and I say X position here, X position is referring to the X position in the big image, but that is not what we need to start writing here for the pixel value of the tiny image. We need to start with 0 value of the tiny image, which means we need to subtract this number from that number in order for it to be 0, right? So that's how we're able to write this image into there. And now if I did the thing, if we say replace target image like this, we will get a replacement in situ from what was our preview. I'm just going to delete the preview. You can see I actually modified the image, and it doesn't even have a different history state. Now this is actually part of the lineage of what happened to this image. That's the cool thing. Now, I had to do this in a number of different ways early on. So I came up with this little expression, right? It's a version of kind of there's a substitute with previews script that was available, but it still requires you to do this awkward thing. And I didn't like that. I wanted to actually write the pixel values just from one image to another without any intermediate steps in between. And so this expression would allow me to do it. And then later I created a much more complicated expression that would actually make elliptical shapes instead of just a circular shape. And you could use those for masks, for example, but it's based on this very same idea. I'll even show you that expression just for fun. Here's the expression. You can see now that I have a variable that holds basically a position angle. That's just an angle there. Then I have another variable which holds the calculation, this thing, that's the function of an ellipse. And then I added this really cool thing which says that if we are within the ellipse, that's what the first statement says, then do this cool thing where you can make a gradient of brightness. So you can go from the outer thing, which is kind of 0, all the way to the center of the ellipse of whatever you drew, and then you will, making it a value of 1, which means you can get this elliptical shaped thing going on there, which is awesome. So just to show you what it does, I'll make this a target T here, and if I invert this image, Control I believe that this should put an ellipse. Yep, just like that. So that's just the ellipse. And if I change the angle here, I can rotate that ellipse around and do other kinds of cool things. But you get the idea, symbols. But you get the idea, 90, yeah. So let's do, I don't know, 23, just for fun. Watch this. So this thing, this expression, eventually was an inspiration and partially used in what became the game script, which is a popular script that many, many people know about. So I started from the idea here and then generalized it to a much more cool thing, which is the creation of ellipses, and that can be used for masks and all kinds of interesting things. Let me just come back here and now show you also that the expression that I made just to insert directly one image into another, it became part of a much even cooler thing, which is another script here, which a gentleman made, and I need to go find it. It is called Substitute here. It's the substitute script, and it does not only the one thing that I just mentioned, but it does, you can use it in a number of different ways, which are all listed here. So just to demonstrate, you know, without having to use an expression now, all you need to do is say source image. I could select this preview in this image, which is the master light. Oh my goodness, that should be this preview right here. And then I say the target image is that image itself without the preview. So the target image would be the master light, this one right here. So we should just be able to press the button and it'll do it. Ready? Okay. And there it is, one step. You just select, you know, your preview, you select your target view. The preview can be adjusted in any way that you want, and then you don't need to do anything more other than just run that script and it'll insert it. But that script uses that same basic formula that I just described. So problem solving again, but a nice way to see how to determine and solve problems using pixel math. Really easy to do. It's particularly informative to go here, look at all of the functions that are available. So you want to think to yourself, you have some problem. How do you solve it? One of the first things to do is go look in the list and try to find something that may be the tool that you need, and then understand how to take advantage of that tool to solve your problem. I hope that you enjoyed this section on this video on pixel math and some of the cool things you can do, solve some problems. It also addresses some misconceptions and ultimately can be a nice innovation in your processing workflow. Thank you very much.
Nice. That was awesome. That was good. All right. Are you muted?
Yeah, not
and your
anymore.
Battery.
Yep, no, I'm good. Oh wow.
Is your battery low? Your battery's flashing.
My battery's
flashing.
flashing.
You got a battery blinking, flashing on your screen.
I don't know how that happens, but that happens sometimes. I'm not sure why that happens.
Okay.
I have a dummy battery in there, but I don't know. That's Canon for you. I don't know.
Yeah, no.
The noise was.
It wasn't me. It was the one-armed man. But
nope,
no, Pixel Math is super.
It was none of us.
It's super, super powerful.
Yeah. So we do have 2 more guests to go, and then the live panel, and then a lot of giveaways.